We've previously talked about the ideal gas law and how to use it. We've talked about how the ideal gas law is used to describe the state of a gas. But so far, we've only talked about pure gases. Now what we're going to do is talk about what happens when you have mixtures of gases and how we can describe those using what's called Dalton's law of partial pressures. Knowing how to describe mixtures of gases is really important because as chemists, we often deal with mixtures of gases. One of the most important and most relevant mixtures of gases to us would be our atmosphere, which is a mixture of many gases, but primarily nitrogen and oxygen. We're going to consider a mixture of nitrogen gas and oxygen gas here. And we'll start by talking about how you would find the total pressure of this mixture. This is called Dalton's law of partial pressures, which says that in the mixture, the total pressure of the gas will be equal to the partial pressure of the nitrogen plus the partial pressure of the oxygen gas. Importantly here, the total pressure for any mixture of gases will be equal to the sum of the partial pressures of all of the gases that make up the mixture. And importantly, Dalton's law of partial pressures makes some key assumptions, one of them being that there are no interactions or reactions between the gas molecules. And so what that means is that, right, the N2 and the O2 are not affecting one another in any way. The pressure of the nitrogen and all of the nitrogen molecules are not affecting the pressure of the oxygen or any of those molecules. Everything is independent. There are no interactions or reactions. And that's how you're able to simply just take the sum of partial pressures to get the total. We're going to take a look at an example problem that's going to involve Dalton's law of partial pressures. And this is another case where it's nice to look at an example that is somewhat complex and talk about how we can break it down into manageable pieces and identify what type of a problem we're working with here. In this problem, we have an apparatus which contains two chambers that are separated from one another by a valve. And initially, in one of the chambers, we have 2 liters of pure hydrogen gas at a pressure of 475 torr. And on the other side, we have 1 liter of nitrogen gas at a pressure of zero point 0.2 atmospheres. So initially, these gases are pure. But what we're going to do now is open the valve and allow the gases to mix. And we're asked to determine what the total pressure in this whole system will be after the valve has been opened. Furthermore, we're told that we can assume temperature is constant, and that will help us in the analysis of this problem. Let's start by trying to figure out what's going on in this problem and what type of a problem we're dealing with here. For one thing, we recognize that we're mixing gases together, and since we're dealing with a mixture of gases, Dalton's law will come into play at some point. The total pressure will be equal to the new pressure of the hydrogen gas plus the new pressure of the nitrogen gas after you're allowed to mix the gases. But also, we have to talk about what else is going on in this problem. Because when you open the valve, let's think about what's going to change. Will there be a change in the state of the gas? Absolutely. And how do I know that? Why is that true? Well, when you open the valve, what's going to happen to, let's say, the hydrogen gas? Is all of it just going to stay in this 2-liter compartment? No. Once you open the valve, the gas is going to expand to fill the full volume of the container. It's going to expand to make a total volume of 3 liters, right? 2 from this side plus 1 from that side. And the same is going to be true for the nitrogen gas. When you open the valve, it will no longer occupy 1 liter of space. It will expand to fill the whole 3 liters. So in this problem, the volume is changing. We're told that the temperature is constant. So then what else has to be changing, right? If temperature is constant and you change pressure, then that means that you have to change the volume. And we can use the change of state equation to see how the pressures of the H2 and the N2 change upon opening the valve and allowing the gases to expand. The change of state equation will be crucial in helping us to find the new partial pressures of the H2 and N2. And again, we're able to determine that this problem is a change of state problem and that we need the change of state equation because in this problem, we are changing the volume of the gas, meaning that the pressure has to also change. So that's how we are able to identify that we're dealing with a change of state. I'm just going to copy the most important information onto the next slide so that we have a little bit more room to work through the answer to this problem. All right, I just copied over a figure of the apparatus with the information the problem has given us, and now let's talk about setting up the problem. We've previously identified that we're dealing with a change of state problem here, and so it's helpful for us to go ahead and write the equation that we have for change of state. P1V1 over N1T1 equals P2V2 over N2T2. And in this problem, we were told that T is constant. And in addition to that, we're not adding a gas into here, right? We're not adding in more hydrogen or nitrogen. We're not removing any hydrogen or nitrogen. And so N is also constant. And that will help us to simplify this expression pretty significantly. We're able to cancel N and T. And that gets us just to P1V1 equals P2V2. And now what we're going to do is treat the two gases separately from one another. We're going to use the change of state equation to find out what happens to the hydrogen and just deal with the hydrogen. And then separately, we'll use the change of state equation again to find out what happens to the nitrogen and only look at the nitrogen. And then at the end of the problem, we can put them together using Dalton's law, right? So that's the great thing about Dalton's law here, is that you can treat the two gases completely separately from one another, so you don't have to be dealing with both of them at the same time. And that makes this analysis a lot less tricky. So for the H2, we can write out that P1 for the H2 times V1 for the H2 equals P2 for the H2, V2 for the H2. And then we can organize the information that the problem has given us. Always a good idea to do that. P1 for the H2 is 475 torr. That's our initial pressure. And the initial volume for the H2 is 2 liters. The final pressure of the H2 is unknown, but that's going to help us get the answer to this problem. So we don't know what that is. The final volume of the H2 is the volume that you get when the H2 expands to fill the whole container, right? That's our total volume of 3 liters here. All right, with that in mind, we're going to solve the change of state equation for P2 of the H2. That will be done by dividing both sides by V2. So the new pressure of the H2 is equal to P1 times V1 over V2. Then we plug in the numbers. P1H2 is 475 torr, and V1H2, 2 liters, over V2 for the H2, 3 liters. Or the liters cancel out, and we're left with the new pressure of the H2 in torr, and it comes out to 317 torr. And that makes sense, right? When you increase the volume at a constant temperature, then the pressure should decrease, and it has. That tells us what's going on with the H2. Now we're going to take a look at what happened to the nitrogen gas. So we'll do the same thing for the N2. And what we'll say is that the initial pressure of the N2 times the initial volume of the N2 is equal to the final pressure of the N2 times the final volume of the N2. And now we'll organize information. The initial pressure of the N2 is given as 0.2 atm. And the problem asks us to find what the pressure is in units of torr. So we should convert to torr now, using the conversion factor that we saw earlier that said that 1 atm is 760 torr. So there we have it. And what we have as our initial pressure in torr is 152 torr. All right, the initial volume of the N2 is 1 liter. The final pressure of the N2 is unknown, but that's going to help us get the answer to this problem. And the final volume of the N2 is 3 liters when, it expands to fill the whole volume of the container. Once again, we're going to solve for P2, and that's done by dividing both sides by V2. And now we plug in the numbers. So we have that our initial pressure of the N2 was 152 torr. times the initial volume, which is 1 liter, over the final volume, which is 3 liters. Once again, the liters cancel out, and I find the pressure in units of torr. The new pressure of the nitrogen gas after it expands will be 51 torr. So we've now found what the new pressures of the H2 and N2 are. The last thing to do is put it all together and find the total pressure in the container. So I'm going to just move things up a little bit to make a little bit more space so that I can finish the problem here. All right, so now we're going to use Dalton's law of partial pressures to get what the total pressure is. Dalton's law says that the total pressure is going to be equal to the sum of the partial pressures. So that's going to be the new pressure of the H2 plus the new pressure of the N2. Therefore, the total pressure in this apparatus will be 317 torr plus the 51 torr that the nitrogen contributes, giving you a total of 368 torr. And there we have it. So once again, it's nice to see problems like this so that you can see that even the most complicated seeming problem can be broken down into manageable pieces. It can be broken down into things that you've already seen before. The idea behind this is, and the key to this problem, is to recognize two things. Number one, you recognize that you're dealing with a mixture of gases, and so the total pressure will be found by summing the pressures of the H2 and the N2 after mixing. The second key component to solving this problem is to recognize that you're dealing with a change of state by noticing that when you open the valve, the volume changes. Since you're changing one of the properties of the gas, you're dealing with a change of state problem. And that also helps you to set up the problem and figure out what the new pressures of the H2 and N2 will be. Up next, we'll continue talking about mixtures of gases, and we'll discuss doing gas stoichiometry when you have mixtures of gases.